Okay, today it's a comparison test. We have two comparison tests we're covering in this video. That's just plain old comparison test. If a series converges by being bound from above by a series that you've already tested to converge, then the series lesser than it would also converge. If you have a series that you're testing that if it diverges, and you can test a series that's always less than for each term that also diverges, then you can show that your series would diverge. You have a second test called a limit comparison test, where the ratio of two limits, one of which has a known convergence or divergence, can help you determine whether your series will converge or diverge. We got examples of each too. So the comparison test, I got three series here. I got C, I figured, for clowns, and J for jokers, and stuck in the middle here is U. If U is the series we are seeking to test convergence, and you have other series that you've already known, such as C of n or J of n, if J of n converges, then it means that the lesser function U of n must also converge to some value. And likewise, from down below, if C of n diverges, it forces the U of n to also diverge, as well as the J of n too. And so that is our comparison test. So whenever each term of the series is lesser than the different one, and that lesser one diverges, it's going to, by being that each term is less than in value, it's going to force the larger valued series to also diverge. The same is true for convergence. So in a way, it actually sort of makes sense. Or at least for me it does. I hope it does for you. So would a series like this converge? Like 1 over cosine of 1 plus cosine of n over n squared. You would, if we want to test it converges, we want to find a value we want to find a different series that's greater than this for every term, and then verify that it converges. And so there's a couple different ways we can find a series that's always greater than that, or is greater than or equal to, is by modifying the numerator or the denominator of what we have into something that's more easy to test. And in this one, it might be easiest to replace, what would be easiest to replace a numerator for our comparison function. The 1 plus cosine of n can never exceed 2. So we can compare it, because cosine of n, the numerator is only going to range from 0 to positive 2. So what if we were to replace this with a series where the numerator is a 2 over n squared? Then you would have a series that is greater than or equal to for each term. And if we can find out if that converges, then we know for sure that our series that's less than would also converge. And yeah, there's these arrows I drew from a previous take. I made a mistake. And so we're testing if this, so we know that each term on this side is greater than the term over here. And so if we can prove that this one does converge, then we know that over here this one must also converge. And so let's take a look at this 2 over n squared. What kind of series is that? It's a p series. And in this case, p is equal to 2. All p series converge when p is greater than 1. And since this series is greater than equal to the series we're testing, we know that that series would also converge. So we've tested it, we've verified because of that. Because this converges, this must also converge. That's how the comparison test works. Does this series converge? We need to find a very similar function that is going to be always greater than this. Now, another way you can always make something greater is to reduce the denominator slightly. And so if you see convergence and you see a +1 or +2 or something in the denominator, that's a hint that, I could subtract that. And especially when you see that it could cause some n terms to cancel out. Those are big hints right there. Because, of course, the homework assignments are probably going to be problems where things will cancel out gracefully. So if you replace the 3 plus 1 with 3n plus 1 with a 3n, then in the denominator would be a little bit smaller, which would cause the whole ratio to be a little bit larger for every term. And because the n's cancel out, this becomes 1/3 to the n power. And what kind of series would this be? You've seen this before. This was in a previous video. 1/3 to the n power. It's a geometric series. And r is equal to 1/3, which is less than 1. The series converges. And so that means that the series we're testing, that's always lesser than, would also converge. So here is our other comparison test in this rather short video, or short compared to most. By taking the limit of this function of known convergence or divergence, you can't test a divergence or convergence of another function by taking the ratio of the limits. That's the limit comparison test. And so it's key that the two series that you're comparing are both greater than 0. If you give this an alternating series, you'll get some really screwed up results. So none of the alternating positive minus stuff for the limit comparison test, because it totally won't work with these. But if it's always positive for each of them, you can do this. You can take this ratio, and so if it ends up being a constant, what this converges to, if the limit approaches a constant and it's greater than 0, we know that a of n, the sum of a of n and the sum of b of n would either both converge or diverge, because they would both have the same end behavior in order to divide to a constant. And so if you're going to be if you do this, you'd better know that whether a of n or b of n, one of the two, would converge or not. Because if you're doing this test and you don't know that, then it would be a slight bit pointless. But if the limit ends up equal 0, in other words, the limit of b of n becomes incredibly large as the limit of a of n becomes smaller, then we have that b of n, that series b converges, and also that would mean that a of n would also converge. Because if the b of n is becoming large, with respect to a of n, and denominator is becoming huge, it may then then for sure the series a of n would also converge. And now if you have the case that when you see infinity, you can probably assume that the word diverge is going to be associated with this. If a of n becomes incredibly large, it's going to need and it's being divided by b of n, which of course is not going to be nearly as large as a of n, otherwise it wouldn't be infinity. But if you show that b of n diverges, well, and this ratio is still infinity, then a of n would certainly be divergent. And so oftentimes we can do algebraic simplifications and then apply the limit. So sometimes you can do that. And so these limits aren't necessarily always difficult. Sometimes you can use your limit laws that you've learned previously to your advantage, like in example C. So does the sine of 1 over n converge or diverge? Well, for the sine function, there is one famous limit from back in Calculus 1. This was towards the middle or the end of Chapter 2, where when you're studying limits, and that's the limit of sine of u over u. It's sort of famous. As u approaches infinity, this limit is equal to 1. And we can use this to our advantage by a substitution of u equals 1 over n. And so the limit as n approaches infinity is equal to 1, because they have the you see what I did there? This is sort of sneaky, and I'll tell you that your homework problems shouldn't be as screwy as this example. The examples I try to make them harder than the homework problems. This limit is equal to 1. And so look at our 1. It tells us that the series is being that it's converges to approaches a value c equals 1, which is not 0, that they would either both converge or they would both diverge. So we know if one of these converges, the other one would also converge or diverge. So we're going to have to test, does the series 1 over n, the n from n equals 1 to infinity, does this diverge or converge? That's if it diverges, then the sine of 1 over n would also diverge. If it converges, then sine of 1 over n will converge. Well, it turns out that 1 over n is a divergent harmonic series. So, in which we did that about 2 videos ago, fairly recently. And so the sum of the summation sine of 1 over n would also have to diverge. Would this converge? This would require some simplification to maybe make it a little bit clear, because we have mixed terms here. We have an exponent here, and we have an exponent here using the more antiquated symbols. And let's put those into the same form. That's n squared, and that's n to the 1/2 power. And we combine those to the same exponent of n to the 5/2 power, or n to the 2.5. Because when you multiply two terms of the same base, the exponents add. So you're adding that 2 plus 1/2 to equal 5/2. So let's see what we did here. So we have this a sub n term, And we compare this to a different series. B of n is 1 over 3 halves. And what happens is that you get a simplification of n plus 1 over n as n approaches infinity. And this limit would converge to 1. So A of n and B of n must either both converge or diverge. So now the question is does 1 over n to the 3 halves converge or diverge? We have to test that against our types of series that we've looked at in the past to determine if this is true or not. It's a p series, and p is equal to 3 halves, which is greater than 1. So this series converges, and so that tells us the other series will also converge. And so that's what this test is about. And so this one was also a fairly bit complicated. It involves some pretty wicked division here, especially the n to the 5 halves being reduced by 3 halves to give you a n to the 2 halves, or n to the 1 in the denominator. It was sort of hard, but not too bad. Anyway, homeworks are up. Play with them. If you have any questions, call me on Skype or give me a phone call or something. You should have fun with this one. All right, well, I'll see you then. We'll go over this also in class.